Hello students, welcome back to my chemistry sessions with you. And now what I have thought of doing with you people is something related to the JEE mains pattern exercise as per you can see on the screen. Right? So let me just give you a review of what all we have done in my previous lectures. I remember we started with the chapter solid state. Having started with the discussion of the chapter solid state, we moved on slowly and slowly with all the different concepts, right? Maybe we would have covered more than 10 lectures, like maybe there must be 11 or 12 lectures that I covered with you people regarding the complete concepts, the theory part of the chapter solid state. But you know guys, until and unless you won't do the question answers, you won't realize whatever theory part we have covered, was it worth it or not, right? And just to give you a kind of idea what kind of questions are basically asked from the chapter solid state, I am gonna consider a few questions. Like I have taken a total of 10 questions from JEE mains pattern. Fine enough. So without wasting any further time, let me directly move on to the very first question. Okay, so this is the very first question that you can see on the screen, and the question says that the sodium metal crystallizes in a body centered. So we are talking first of all about the sodium metal, okay? And this sodium metal is known to crystallize in the body centered cubic unit cell, okay? And we are also given that the edge length is 4.29 angstrom. And you simply need to find out the radius of sodium atom is approximately. These are the four options which are given to you. We just need to consider the radius of sodium atom, and that too as an approximate value, right? So let me write it down like how the solution is to be done. First of all, he has mentioned only and only sodium metal. So we have sodium present as a particle, sodium only, it is present just as an atom. It is not an ionic crystal. So we are not considering any ionic crystal, okay? And the other option says that it is a body centered cubic unit cell. What is body centered cubic unit cell? You know, right, in the case of body centered cubic unit cell, we have the atoms which are present where and where? They are present at the corners, plus one atom is also present at the center of the body, okay? And he has also given us that the edge length is given to be 4.29 angstrom. And we simply need to find out the radius of sodium atom, right? Now guys, if I draw the body centered cubic unit cell, you must be okay if I draw it like this. So there is a cube which I'll consider. So it's a cube like this. Then all the atoms are present at the corner. So the white ones are the sodium atoms which are present at the corner, and they are not touching each other. Plus, you know, right, there must be one atom which is present at the center of the body, and this atom is touching all the four atoms on the top and also all the four atoms at the bottom, right? That is why it is present at the body centered. Now you can very easily say that if, see, let us try to figure out the length of body diagonal. So let us assume the edge length which is given to be A. This is also A. So if this and this are A and this angle is 90 degrees, so you can use Pythagoras theorem, and when you can use Pythagoras theorem, you will be able to find the length of this blue line. So this is A, B, C. So AB and BC are given to you as A. So you can easily find out AC square will be equal to AB square plus BC square, the simple Pythagoras theorem, which will be A square plus A square, that is 2A square. So finally what you will get? You will finally get the value of AC as under root 2A. Point number 1. Now once you know that this length is under root 2A, you also know that this length, let me call it to be CD. This is given to as edge length A. Again I can ask you, right, that you can consider the Pythagoras theorem. So if you consider the Pythagoras theorem in this particular triangle, and this AD is what? It is the body diagonal. So what you should be getting? You will finally be getting the value as under root 2A square plus A square will be equal to AD square. Am I right? So you can say AD will be equal to under root 3 times A. So this is the length of body diagonal. Okay, and if I am considering it's a body centered cubic unit cell, one atom will be present here, one atom will be present here, one atom will be present here, right? And if I now ask you to get the total, R. So you can simply say that under root 3A can be written as 4 times R. Am I right? This is what we do for body diagonal unit cell. Then we have under root 3 into A. What is the edge length given to us? The edge length that may be given to us is 4.29 angstrom. 2b divided by 4, you will get the value of R. And if you calculate the value of R, you will finally end up getting the value of R as 1.86 angstrom. Guys, I am a very good student of maths also, so I know the answer like this, right? But for you people, you need to do the calculation. So under root 3 is 1.732. To be multiplied by 4.29 divided by 4. So what you will do? Just take it to be 1. So 1 into 1.732 must be something related to 1.732, right? But little more than that. Now see. This is 3, this is 5, this is less than 1, so not even this. So the only best option which is an approximate answer is option number A. And this was our first question for this particular exercise. Note it down so that I can simply move on to question number 2 as well. Note it down, guys. Okay guys, so I think you people are done with this particular question. So once we are done with this question, I think we should move on to the second question. Okay, so just give me a sec. Let me clear the board for you so that you can easily visualize question number 2 as well. So for question number 2 that I have chosen for you people is, we have cesium chloride, CaCl. It crystallizes again in a body centered cubic unit cell. So that means the diagrams that I have drawn earlier, they will be useful for me again. So so we have cesium chloride, and this is known to crystallize in body centered cubic unit cell. If A is the edge length, this is what we have done, A is the edge length, then which of the following expressions will be correct? So we need to find out whether the radius of cesium plus Cl minus will be equal to 3A, or will be equal to 3A by 2, or will be equal to root 3A by 2, and so on, alright? Okay, but the question is, how will I be able to do the question? The question can only be done if you know the structure of cesium chloride. So what exactly is the structure of cesium chloride? If you know this thing, then you will be able to solve the complete question as well. Now, how should I be beginning with this particular question? Listen to me very carefully. When I am talking about the crystal structure of cesium chloride, you remember I have told you in my lectures as well that in the case of cesium chloride, the chloride ions will be present at the corners. So they will be present only at the corners in the case of a primitive unit cell. So they must be present in the primitive unit cell, normally at the corners. And the cesium plus is present at the body center. So see guys, what is the difference in this question and the earlier question? Like when I was talking about the earlier question, I said that all the atoms which are present at the corners and at the body center were same. That means earlier sodium atom was present both at the corners plus at the body center. Right? That means it was just the sodium atom which was present at the corners as well as body center. But now what I am saying chloride ions are present only at the corners, whereas cesium plus is present at the body center. So this CaCl is a kind of ionic crystal. Okay. That means if I ask you to continue further, come here to this particular picture that I have drawn. So if you are coming here to this particular picture, I can color the atoms. So this particular atom, the one which is colored in white, is the cesium ion. Cs plus, okay, whereas the other two that I'm gonna color in pink, let's say I'm coloring this one and I will also be coloring the other one, which is this one. Now these two are known as our chloride ions. Okay, so these are what? These will be known as chloride ion. Cl minus. Okay, again guys, we are gonna use the same expression. See carefully, we will be using the same expression, but this time I will say the length of the body diagonal. What did we find the length of body diagonal as? We found out it to be under root 3 times A. But this will be equal to radius of chloride, R of Cl minus plus what? Radius of cesium. Once again plus R of cesium again. Plus once again R of Cl minus. Am I right? So what did we finally get? We will finally be getting under root 3a by 2 is equal to radius of cesium plus plus Cl minus. Let's see if this matches the options which are given to us. Come over to the options. So in the options we have R of Cs plus is equal to 3a, no. 3a by 2, no. Under root 3a by 2, that's the correct answer. Yes guys, so we have got option number C as the correct option for this particular question. Note it down so that we can finally move on to the third question as well. Note it down very carefully. Okay guys, having done with the second question, it's the time I should be moving on to the third question. And the question says that experimentally it was found that a metal oxide has the formula M0.980. See guys, if there is a metal oxide with the formula M0.980, now you must be okay if I say that this will be belonging to non-stoichiometric defects. Right? Because see, we do not have an exact formula. So if the exact formula is not known, I can say this is an example of non-stoichiometric defect. Okay, so that is of no use to me in the question, but I just told you as a revision part. Now he is saying that the metal M is present as M2 plus as well as M3 plus. This metal is present both as M2 plus and M3 plus. So what is the fraction of metal which exists as M plus 3? So he is basically asking you for M plus 3. Let us try to figure out the answer. So guys, I remember we have done a similar question in our theory part as well. So what we used to say, let us say if the metal oxide is given as the formula M0.980, I can very easily multiply with it with a factor of 100 and finally my answer will be M98O100, right? That means if I am having 100 atoms of oxygen, right? If I am taking a total of 100 atoms of oxygen, I can take a total of 98 atoms of metal. Okay. Oxygen is always present as O2 minus in the case of oxide. So what is the total charge? Total negative charge. Total negative charge will be 2 minus into 100, making it a total of 200. So this is the amount of total negative charge. Okay. Now let us try to consider what is the amount of total positive charge which is present in the metal. Now guys, see, there are 98 atoms of metal, but the metal is present in both +3 as well as +2 oxidation state, right? So can I say consider X atoms of M2 plus might be present and the remaining will be 98 minus X of M3 plus will be present, right? So let us now try to figure out the total positive charge. So what should be the total positive charge? So we can say that the total positive charge will be X multiplied by 2, which is 2X, plus there will be 3 charge on 98 minus X atoms. So this is the total positive charge. And we know that for the metal oxide to be neutral, guys, see, this metal oxide is having a 0 charge. Overall it is neutral. So can I simply say that the total positive and the total negative charges are same? And if I say so, I can write 2x plus 3 into 98 minus x will be equal to 200. Again, I am a calculator, and since I am a calculator, I can solve it easily. You will get the value of x as, let us try to calculate the value of x. So the value of x will be obtained as 94. Okay. So don't simply say that, ma'am, m plus 3 will be 94%. It's gonna be a wrong option, guys. You remember, listen very carefully. We have taken, there are x atoms of m plus 2. That means 94% of metal is there in +2 oxidation state. So how much will be there in +3 oxidation state? We can say 98 minus 94, which will come out to be a total of 4%. Okay, let us see if there is an option which is given to us. So I am just trying to figure out the simplest, easiest way answers. So this is 7, 4.08, 6, 5. So the answer will be B, which is the correct option. Okay. Now having done this, let us move on to the next question. Please note it down so that we can continue further. Okay guys, having done this much, let us now directly move on to our next question. And the question that I have chosen for you people was this one. This question has again been asked in past year JEE papers. Let me read out the question for you. The question says that which of the following exist as covalent crystals in solid state, right? Question is, which of the following exist as covalent crystals in solid state? Guys, you remember we have done the crystalline. Were divided into 4 different categories, and the very first was ionic crystals, which were made up of ions. Do we have any ionic crystal in the examples? We have iodine, silicon, sulfur, phosphorus. No, there is no ionic crystal. So ionic crystals are gone. Then after that we had amorphous substances, but these are not crystals, so let me just remove the case of amorphous because they are separate class, right? So let us just ignore them. After this we moved on to metallic crystals. Metallic crystals, their constituent particles were what? They were metals. So let us see if some metal is there. Guys, iodine is a non-metal, silicon is a non-metal, sulfur is a non-metal, phosphorus is a non-metal. So none of them can be considered as metallic crystal as well. Coming on to the third category, I remember teaching you another category as molecular crystals. And there was one fourth category, and this fourth category was known as are covalent crystals. Covalent or network crystals. So let us try to figure out which example suits these two classes. Molecular crystals were basically those which were made up of molecules, right? Whereas covalent crystals were those which were made up of atoms, but then they had a huge network structure. Am I right? Moreover, when we were talking about the covalent crystals, I remember telling you people that they have covalent bonds, right? Whereas if I am talking about molecular crystals, the two molecules may be attracted to each other with the help of dipole-dipole interaction, or maybe with the help of ion-induced dipole interaction, or maybe with the help of just van der Waals interactions. Right? Let us try to figure out the cases now. Point number 1 is our iodine. Guys, iodine is a molecule which exists as I2. So there may be so many molecules of I2. So this will be forming the molecular crystal. So iodine is an example of molecular crystal, not the example of covalent one. Moving further, consider phosphorus as well as consider sulfur. So they are typically non-metals, right? They will also be existing in the form of molecules. Like sulfur exists in the form of S8, phosphorus exists in the form of P4. Fine, because they have tendency to form bonds with itself, but P4 will be formed. S8 will be formed, which is a molecule. However, if you take into account another atom which is silicon, guys, if you see the structure of silicon, it actually exists as dense network or covalent solid. You must have considered the cases of silicon compounds. You must have considered silica, which is sand. So all of these things are available in nature in the form of covalent crystals or network crystals, and hence making option number B as the correct answer for this particular question. So quickly note it down so that now I can move on to the next question, which is question number 5. Okay guys, having done with this particular thing, let us move on to question number 5 now. Let us see what's the question there in store for you. So question number 5 says that, okay, in the FCC unit cell, what fraction of H is not covered by atoms? So first of all, I have no idea, but the only thing that is given to me is face-centered cubic unit cell. So if he's talking about face-centered cubic unit cell, I can draw the structure like this. Right? So there must be an atom which is present at the center of the face, which I'll draw something like this, and there will be 4 atoms which are present at the corners. So let's draw one atom like this, one atom like this, one atom like this, and one atom like this. This is something related to face-centered cubic unit cell, right? Now he is saying in the FCC unit cell, what fraction of edge is not covered by atoms? That means he is asking us to find this white length divided by the whole edge length. The whole edge length is this. Okay, so this is what you have to find out. What you have to find is the white length to be divided by the edge length. So that's a question that we need to consider. Now guys, let us try to figure out what is not covered. This whole length is A, which is edge length, right? And this distance is the radius, this distance is the radius, but the two are not touching each other. So what is not occupied? You can say, right, if I take A and subtract 2 times R from it, this is actually the white length. See guys, if I am right, this is total is A, subtract R, subtract R. So A minus 2R is nothing but this white thing, which is the uncovered portion. Fine. Also, what is the edge length? Now we have the edge length as, so what is the value of edge length? The value of edge length is A. Okay. So what we need to find out? Our answer will be A minus 2 times R to be divided by A. But guys, see, if there is an option like A minus 2R by A, no, the options are only some values, right? So first of all, we need to know the relationship between A and R so that both of them can be interconverted to each other, right? So what can I say? Look at the figure again. This is under root 2A. This is what we have done now, the length of face diagonal. So we know, right, the length of face diagonal will be equal to under root 2A, and under root 2A will be equal to what? R plus R plus R plus R, R. So root 2A is equal to 4R. So this is one relationship between A and R, and I can simply say A is equal to 2 root 2R. So if A is given to you as 2 root 2R, I can ask you to substitute the value here. You will get A minus 2R by A, which will simply come out to be, A will be equal to 2 root 2R minus 2R divided by 2 root 2R. Am I right? And if you solve it, see guys, you can take out 2, which is common. So you will get under root 2 minus 1 divided by root 2R. And this value will come out to be something related to 0.293 R. So this, see, R by R is there, so R and R will get cancelled, and finally you will get the value as 0.293. Let's see if there is any such option in the question which is given to us. So we have 0.134, no. We have 0.24, no. We exactly have the option 0.293 and none of these, no. So we can simply say that option number C is the correct option for this particular question as well. Right? Let us now move on to next question, but before that I want to clear the board so you can note down the question. Note it down carefully. Okay guys, I think everyone is done with question number 5. So half of the lecture is done. Let us move on to the other half part of the lecture where we need to start from question number 6. So let's see what is question number 6 for you. Oh wow, there is a cute figure for you, and question number 6 says that the packing efficiency of a two-dimensional unit cell shown below is. So let us consider the edge length as L. Because nothing is given, so I am just considering it L, and let us consider the radius as R. You know, so many students have a problem. They will see, oh ma'am, this is a face-centered cubic unit cell. Because see, so that's a face, at the center of the face there is an atom. So it's face-centered cubic unit cell. And once they know that it is face-centered cubic unit cell, they will easily mark the answer as 74.05% because that is a packing efficiency of FCC, right? But guys, there is a problem in that. Okay guys, so what I was saying was, like I was telling you, so many people will look at the figure, and when they look at the figure, what they'll say? They'll simply say, if you look at the figure, there is an atom at the center of the face, and if there is an atom at the center of the face, you will consider it to be a face-centered cubic unit cell. And if you consider it to be the face-centered cubic unit cell, what are you gonna say? You'll say, ma'am, the obvious answer will be 74% because we have mugged it up like anything that for face-centered cubic unit cell, the packing efficiency is 74%, right? But this is gonna be a wrong answer, okay, because it is a two-dimensional square closed packing. It is not 3D, it is not face-centered cubic unit cell. Fine enough? So what is to be done now? We need to find the packing efficiency of this 2D thing. When it was 3-dimensional, we used to say the volume occupied to be divided by the volume available multiplied by 100. But this volume term was only and only for the 3-dimensional cases. Are we doing 3D case now? No guys, we are just doing the 2-dimensional. And for 2-dimensional square closed packing, you can simply say that the packing efficiency is written as the area occupied divided by what? Divided by the total area available to be multiplied by 100. That's it. Now let us see. So this is the figure which is given to us. How to figure out what is the area occupied? So don't you think area occupied will be this plus this plus these plus this. That means now if you club all the 4 areas, it is nothing but giving you a circle, right? And the area of circle is what? Pi r square, because r is the radius of the circle. Also, there is another area occupied which is itself a circle of the same radius r, plus pi r square. So this is the area occupied divided by, what is the area available? Can you say this is L into L? So the area available is L square, right? I can also consider the edge length to be A. So this can also be considered to be A square. Fine. So we will be getting the answer as 2 pi r square divided by A square into 100. Okay. Now guys, again we need to find out the relationship between A and R. So if you need to find the relationship between A and R, can you simply say that R plus R plus R plus R? That means 4R will be equal to A square plus A square. So that means will be equal to under root 2A. I have used the Pythagoras theorem again. So the length of face diagonal is root 2A. So root 2A will be equal to 4R using the relationship here. So we have under root 2A is equal to 4R. A is equal to 2 root 2R. So we will get 2 pi r square divided by A square. A square will be 2 2s are 4 into 2, 8 into r square. So we will get 2 pi r square to be divided by 8 r square. R square will get cancelled and we will finally get the value as pi by 4. And if you solve it, guys, this is very common value. You solve it, you will get the answer as 78.54%. So answer is not 74%, answer is gonna be 78.5%. So don't mark option number C as the answer, rather you should be very clear that option number D is gonna give you the correct answer for this particular question. Okay? So having done this, let us directly move on to question number 7th. Let's see what the question says for you. Okay, so the question that is there for you guys is there is a substance AXBY that crystallizes in a face-centered cubic unit cell lattice. So this is face-centered cubic unit cell, or FCC lattice is available with us. Okay, and the substance is written with the formula AXBY. Now it says that in which the atoms A are gonna occupy each corner of the cube. Atoms A occupy each corner of the cube. Let us see how many A atoms are available. So they are present at corners. So how many corners are there? There are 8 corners. So the point is 8 into 1 by 8, which will come out to be 1. That means overall there is just 1 atom of A. Okay, and the atoms B occupy the centers of each face of the cube. So B atoms are present at face centers. How many face centers are there? There are 6 faces, each with a contribution 1 by 2, making it a total of 3. So can I simply write AXBY, which corresponds to A1B3, which corresponds to AB3. Let's try to figure out if there is an option. So identify the correct composition of the compound. Oh my god, I love the questions where option number A is the correct answer. So this is option number A, giving you the answer as AB3. Okay, so guys, this was about our question number 7th. Having done this, I will be moving on to question number 8 for you people. So let's see what is there in store for you again as question number 8. Oh, that's a small question. Question number 8 says that the coordination number of a metal crystallizing in hexagonal close packed structure is. So you are given HCP structure. So in the case of hexagonal close packed structure, we have the pattern AB, AB, AB pattern, and so on, right? We need to find out the coordination number of the metal which is crystallizing in HCP. So how to draw AB, AB close packing structure? See carefully. And do remember it's a hexagon. So can I simply write one atom is there in the center, which is surrounded by one atom here, one atom here, one here, one here, one here, one here, forming a kind of hexagon. Then at the bottom end, so this is structure number A. Then in the second layer, we'll say that is structure number B. Then again we have the same structure layer as structure number A. How to draw this? So consider one atom here, one here. Right? So you can see there is the formation of a hexagon. How can I show the formation of hexagon, guys? See carefully, and the layers are A, B, A, B, A, B, and so on. So this is again layer number A. How to draw layer number B again? B. So this will continue and this will continue. Am I right? So we now need to figure out what should be the coordination number. Let us consider the main atom as the yellow atom. So this is my main central atom. Let us see how many atoms are further in contact with the yellow atom. So we have 1, 2, 3, 4, 5, 6 atoms are there in the same plane. Then we have this one as a 7th, 8th, 9th, 10th, 11th, 12th. That means to this yellow atom which is present in the center of the hexagon, 6 atoms are lying in the same plane which are directly touching the yellow atom. 3 atoms are lying above it and 3 atoms are lying below it, and thus making it a coordination number of 12. Again, I am in love with the question because option is A, right? So this was our question number 8 that we have completed. Take a minute or so that now I can move on to question number 9th as well. So let's see question number 9th. Is it a difficult question or an easy question? So guys, all these questions are up to JEE mains level. Fine. Moving on to question number 9th. Which of the following FCC structure, so again it is face-centered cubic unit cell, which contains the cations in alternate tetrahedral voids? Let me read out the options. We have NaCl, but I am very sure that when I taught you the structure of NaCl, we knew that sodium Na plus was present in octahedral voids. So this is not gonna be our answer. When I was talking about the second structure which is of ZnS, I again remember in the case of ZnS, S2 minus are forming the FCC. That means they must be present at the corners plus at face centers. So when they will be present at the corners plus face centers. So how many such atoms are there? So we'll have a total of 4. So when we have a total of 4 S2 minus, how many Zn2 plus do we need? The Zn2 plus that we need should also be 4. You remember I told you that this time the Zn2 plus will be present in half of the tetrahedral voids. So if you want to see these things again, this I have recorded in my lecture as well. How to remember the structure of NaCl, ZnS, Na2O and CaF2, right? So you can refer to the video and you will finally end up getting the answer as ZnS. Option number B. Clear enough? Okay. So having done 9 questions of JEE mains pattern, I finally need to move on to the last question of the lecture, which is question number 10. Okay, let's see what question number 10 says to you. Question number 10 says that a solid is formed and it has 3 types of atoms, atom X, Y and Z. Okay, there is a solid which is made up of 3 types of atoms, atom X, Y and Z. X forms a face-centered lattice with, okay, so X is forming the face-centered lattice, face-centered cubic unit cell. So if X is forming the face-centered cubic unit cell, it must be present at the corners plus it should be present at all face centers, right? How many corners are there? 8. and the contribution at each corner is 1 by 8. How many phases are there? There are 6 phases. Contribution is 1 by 2, making it a total of 4. So this I am very sure that for x I will be writing 4. Okay. So if it is a face-centered cubic unit cell with the total number of atoms per unit cell are 4. So what should be the number of octahedral voids? Octahedral voids should be 4. And what should be the number of tetrahedral voids? So tetrahedral voids are double, so the number will be 8. Let us read the question. Y atoms occupying all the tetrahedral voids. So if Y atoms occupy all the tetrahedral voids, so can I say there will be 8 Y atoms at all? Okay. And the Z atoms occupying half the octahedral voids. How many octahedral voids are there? 4. So half of them, that means 2 of them will be occupied by Z, making the new complete formula of the compound as X4 Z2 Y8, right? I can also consider it to be X2 Y4 Z. So we have X2 Y4 Z, and let us see if there is something else as well. So let's just see, let's read the question once again. A solid is formed and it has 3 types of atoms, X, Y and Z atoms. X atoms are forming face-centered cubic unit cell. So X atoms FCC, that means corner plus all the face centers. That means 8 into 1 by 8 plus 6 into 1 by 2, making it a total of 1 plus 3, that is 4. So we finally get the value of X as 4. Now moving further, we have Y atoms occupying all the tetrahedral voids. So if there are octahedral will be 4, tetrahedral will be 8. And if Y atoms are there in all the tetrahedral voids, so it should be Y8. This is also confirmed. So we have written X4 Y8. Let me write it down again. So till now we reached X4 Y8. Let's see how many Z atoms are there. Question says that the Z atoms are occupying half the octahedral voids. There were 4 octahedral voids, out of which half, that means only 2. So Z will be 2. So we will simply say X2 Y4 Z is the final answer. Let us see. So there will be 2X atoms. So this is X, Y2, Z, X, Y2, Z4, X4, Y2, Z, X4, Y, Z2. So guys, the final answer, it may not be there in the options because of some misprinting, but then the final answer of the question will be X2, Y4, Z. Fine enough? So here we are done with a set of 10 questions which I have taken from past year JEE mains exercise. Some of the questions were those which have already been asked in exams, and some of the questions are those which are like quite probable to be asked in exam, because these are the level of questions which will be asked to you in JEE mains paper. Okay, I hope you would have understood all these 10 questions, the concepts that I have used in order to explain the questions. In case of any doubts, you can please feel free to contact me anytime. Watch the recordings very carefully, make yourself ready enough so that we can now move on to the next exercise, which may be JEE Advanced or CBSE level. So let's see what is there in store for you for my next lecture. Till that time, take care. Bye-bye.